we're first going to talk about the constructor and the fields that are part of PhraseMatchSpliterator. PhraseMatchSpliterator is the only thing that differs really in any appreciable way from the search with parallel streams example we looked at earlier and the search with ParallelSpliterator example we're looking for now. And that's cool because we were able to get this speed up by just changing one part of the software. This should look very familiar because it's basically review. The fields are essentially identical with our earlier discussion of the search with sequential streams PhraseMatchSpliterator. And so this will go fast. So the search stream gang uses this PhraseMatchSpliterator, and it works either for sequential or parallel streams, works the same. Well, it doesn't work the same, but it has the same behavior in both. Earlier we focused on the sequential version, and we'll review some of those pieces briefly just for completeness. We're going to focus now on the parallel version that does these things in concurrently. And the whole purpose of this, so you'll see the big picture, is to optimize the performance because we want things to run even faster if possible. This, again, is just a recap of where this shows up in the overall structure of the program. So recall we have these phrases. We're going to search for the phrases in parallel. And then for each phrase, we're going to break the input up into chunks and search the chunks of the input string, the work of Shakespeare, for a given phrase in parallel. So that's where that's going to go get run. Here's what this kind of looks like. Let's assume that we've got all the works of Shakespeare, and we're trying to find the famous quote from Hamlet, "Brevity is the soul of wit," and we don't know where that appears for whatever reason. So we would search, and as you can see, "Brevity is the soul of wit" shows up at this index from the start of the play Hamlet. And the way this is going to work is the splitterator is going to split the input up into multiple chunks and search them in parallel. So this is what might happen if it's a sequential search. But if we're going to do a parallel search, then this chunk and this chunk can be searched in parallel. Now, obviously, we won't find that phrase in this chunk, but we will find it in that chunk. And because we did it in parallel, we should find it in roughly half the time because we don't have to search through the entire chunk in one thread in order to find it. Yes, Gavin? Good question. I'll show you how that works. It's a special little trick that we use in our splitterator. The question was, how does it know what index it's at if you're searching in parallel? And the way that the program works is it keeps track of the offset of each parallel chunk so it can figure out where the index is in absolute terms, even though you're searching it relatively in one chunk. That's a great question. The whole trick here is to make these splits be done evenly and efficiently. We really want to try to split the input basically in half and keep splitting it in half till it reaches some minimum size. Now, we have to be careful because if we do the splits incorrectly, then we can end up accidentally splitting the input up across the phrase, in which case we're never going to find it, right? Because if we made one chunk that looked like this and another chunk that looked like that, and then we search for "brevity is the soul of wit," wouldn't be found here, and it wouldn't be found here, and that's because it was spanning or splitting across the chunks. So that's one of the things that's going to be the tricky part of writing this whole splitterator, is making sure we never split the chunks across a phrase. And that turns out to be really tricky, but it's very cool to see how it works. Okay, so that's really the main issue here that takes some thought. So let's take a quick look at the fields. This is basically a recap of what we had talked about before. The PhraseMatchSpliterator is an interface that defines a bunch of methods, including try advance and try split. And this particular implementation uses a Java regular expression, takes the phrase, turns it into a regular expression, and then it goes ahead and creates a stream of search results, result objects that will say where a given phrase occurred in the input string, what index it appeared at, if it appeared at anywhere, of course. These are the same fields that were used for both the sequential and the parallel use cases. You'll see that some of the ones we talked about before in passing for the sequential version, and I said they don't really matter now, they're going to be used here, and one of them actually addresses Gavin's question about figuring out where the offset goes, and that's this flag, this field here that keeps track of the relative start of the offset once we've broken things up into chunks. And you'll notice that some of these things are final and some of them are not, and the ones that are not final are actually updated in the try split method. So real quick, this is again recap. M input is a character sequence that consists of all the text in a single work of Shakespeare, like Hamlet or Julius Caesar. M phrase is the given phrase that we're searching for in the work, like to thine own self be true, or brevity is the soul of wit, or et tu brute, pick your favorite Shakespeare phrase. Pattern is that phrase converted into a regular expression. Then the pattern matcher is an association of that regular expression with the input string we're searching with the work of Shakespeare. So it creates a pattern matcher that can efficiently find whether the phrase occurs anywhere in that input. And now we get to a couple things that are relevant for parallel streams. M min split size is used by the splitterator to decide when we've split the string up enough and we can process it sequentially henceforth. So it basically is an indication, don't split things any further. And then the last thing is this offset, and this is used to make sure that the right index is returned relative to the original input string. So we keep track of that so we know where the input string would occur had we done a sequential search. And this value is reset by each splitterator to account for the fact that we've broken the input up into chunks. Okay, so that's basically the fields. That was pretty much a recap of what we had talked about before.